we're going to move on from graphing our parametric equations, and we're going to start taking a look at how we do calculus operations with parametrics. And the first one we're going to look at is a derivative, and it's actually really easy to derive the derivative for a parametric. Now, you could start with your dy dx, which is your basic definition of a derivative, okay, or notation. And what you could do is you could just divide both by dt. And this is going to be how to find the derivative of a parametric. So you just take the derivative of y with respect to t, and then divide that by the derivative of x with respect to t. And we know that that gives us the instantaneous slope at a given point, rate of change. We can also do tangent line problems, optimization. So all kinds of stuff now we can do with parametrics. So let's take a look at an example of being able to find a slope and a tangent line. So we're given this parametric, and we're given this point, t equals -1, and we're going to find the slope at the given point, and then to find the equation of the tangent line. All right, so first things first, let's figure out what's going on with the parametric exactly at t equals -1. And so x is going to be equal to -1 squared minus 3, which is going to be a -2. And then y is going to be equal to -1 to the 4th plus -1, which is 0. All right, so basically in Cartesian coordinates, we're looking at this point right here, and we're trying to find the equation of the tangent line. Now we're going to find dy dt dx dt, and that's going to give us the slope. So dy dt, we're just going to take the derivative with respect to t, and that's going to be 4t cubed plus 1. And then we're going to take the derivative of x with respect to t, and that's just going to be 2t. Now we're going to evaluate that when t is equal to -1. Okay, so that's going to give us 4 times -1 cubed plus 1 divided by 2 times -1. I believe that's going to work out to be 3/2 because we get -3 over -2, which is going to be 3 over 2. And this is our slope at the given point. All right. Now, at this point, we could just use our good friend y minus y1 is equal to mx minus x1. We're going to use -2 as x1. We're going to use 0 as y1 because those are the points when we substitute t is equal to -1. And then clearly we're going to use 3/2 for the slope. So now we get y minus 0 is going to be equal to 3/2 x minus -2. Okay, just again by substituting these values back in for x1, y1, and then this back in for the slope. If we clean this up, y is going to be equal to 3/2 x plus 3. Now, to see if this makes any sense, let's graph the original parametric and then also graph the tangent line on the same graph. And I'm going to use foo plot for this. Remember, our parametric was t squared minus 3, I think. Let me check that just to make sure I'm not lying. So it was t squared minus 3 and then t to the 4th plus 2. Okay, so t squared minus 3 and then s to the 4th plus s, and I know it's t's, but we have to put in s for foo plot. All right, so kind of looks like a rubber band a little bit. Okay, so that's what our function looks like. We could certainly change this. All right, so I could do like -6 to 6, and it's still going to be the same. Now I'm going to add a function in here, right? And the function we're going to add is going to be 3/2 x plus 3. All right, now check this out. Exactly at the point -2, 0, okay, that's what our tangent line looks like, okay? And that's precisely what it should look like. It should be touching precisely at this point. As we zoom in, as we expect with any sort of linear approximation or local linear approximation, the tangent line and the functions seem to have the same behavior as we zoom in. But as we zoom out, they start having a little bit more, there's more error between the tangent line as well as the parametric. So that's one implementation of getting the tangent line, is to be able to approximate the value of the parametric around that point. A second example we can look at this time is trigonometric. Okay, so we have x is cos t plus sine 2t, and then y is sine 2t. All right, So let's see if we can find the equation of the tangent line. Again, we're going to substitute t is equal to 0. And when t is equal to 0, this one's pretty easy. We get x equals cos of 0 plus sine of 2 times 0, which is going to be 1 plus 0, which by multivariable calculus methods is 1. And then y is going to be sine of 2 times 0, which is 0. Okay, so we're looking at the point 1, 0 on our graph. All right, so now what we can do is we can go ahead and find the derivative. So we're going to find dy dt and then dx dt. And we know that the derivative of cosine is minus sine. Then we have the derivative of sine 2t. That's going to be 2 cos of 2t by using our chain rule. And then in the denominator, we have another 2 cos of 2t. And remember, we're looking at the point when t is equal to 0. So if we substitute that back in, we get negative sine of 0 plus 2 cos of 0, 2 times 0. All right. And then finally, we can divide by that by 2 cos of 0. Okay, so let me just write that out a little bit better. Okay, and then we're going to divide by 2 cos of 0. We know that sine of 0 is 0, cos of 0 is 1. So this winds up being 2 times 1 divided by 2 times 1, which is 1. And that is our slope at the point. So if I'm answering part A, where we're asked to find the slope is 1. Now we can go ahead and just find the equation of the tangent line, which is pretty easy. Y minus y1 is equal to mx minus x1. We know that 1 is x1, and then y1 is going to be 0 for us. So we get y minus 0 equals 1x minus 1. And then that just yields y equals x minus 1. One more time, we want to make certain that we are okay with what the outcome of this is. Okay, and to check our answer, we can certainly use technology. So remember our original function, cos sine 2t divided by sine 2t. All right, so x was cos of t plus sine of 2t. And then we had sine of 2t, or 2s, sorry. So I forgot to use s instead of t, otherwise we don't get anywhere. Okay, so we get this sort of silly looking thing here. It's like an hourglass that's been crunched up a little bit. Remember, we had x minus 1 for our function. And remember the point that we were looking at. If we go back, we were looking at the point 1, 0. And so if we go back finally to the graph of this, once again, we have a really nice tangent line that can be served as a local linear approximation at the point t equals 1 or t equals 0 or the point 1, 0. Okay, so that's our equations of tangent lines. Pretty easy to do. A couple extra steps than what you might have done in Calc 1, but nothing overly rigorous. Okay, so in our final section, what we're going to do is we're going to look at how we can use calculus on parametrics to be able to find arc lengths.